Okay, I think it's time to get started. And also I started a recording of the seminar. So hello everyone, welcome to the Space at VT seminar. And since Kevin is out today, so I will be hosting the meeting on his behalf. So let's get started by introducing our speaker today, Dr. Samantha Perry Kenyon. Hopefully I pronounced your name correctly.
That's correct, yes.
Thank you. So she graduated this August from the University of Florida with a PhD in aerospace engineering. She did her graduate research work in the Precision Space Systems Laboratory, working primarily on developing technology for the Laser Interferometer Space Antenna mission, which she will be talking about in today's seminar. And she received her bachelor's degree in mechanical engineering, minor in astronomy from Grove City College in Pennsylvania. She is a recently hired faculty research associate with Space at VT. So welcome, Sam. I think the floor is yours now.
All right, great. Thanks, Sherning, for the intro. Thank you all for coming, taking time out of your schedules to hear this talk. I hope that you learned something new and maybe get you interested in gravitational wave research, which is an up and coming field in astronomy, a new way to learn things about our universe. So it's pretty exciting. I'll be talking to you about the LISA mission, which LISA stands for Laser Interferometer Space Antenna, to detect gravitational waves in space. I'll be talking a lot about the basics of the mission, how it works, the type of science it'll do, and then I'll briefly talk about the work that's being done at the University of Florida that I got to be a part of to make this mission possible. So with that, let's get started. Okay, so what exactly is a gravitational wave? It is a strain in space-time, or you can think of it as like a ripple. If you think of space-time, say, as a flat pond of water, and you were to drop a pebble, and there would be waves in that water kind of radiating from that source, that's basically what a gravitational wave is, and the water surface is space-time. This phenomenon, gravitational waves, was predicted in Einstein's theory of general relativity, where he noticed that mass isn't always conserved during big high mass merger events. And this energy is converted into a gravitational wave through his equation E equals mc squared. So in order to observe a gravitational wave, we need to place, at least have two test particles in free fall, and then we can measure the separation between the particles as a gravitational wave passes through. So we have a horizontal direction of change and then also a cross direction. You can kind of see this animated here in this graphic on the bottom right. You kind of see this, if space-time was a grid, gravitational waves kind of rippling through that grid structure. Okay, so we have a ground-based gravitational wave observatory called LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. Some of you might have heard about this instrument, but LIGO right now has two locations, one in Hanford, Washington, and one in Livingston, Louisiana. And the two centers basically communicate their data findings with each other to either confirm or deny that a certain signal was indeed a gravitational wave. They should both be able to detect it. This helps with filtering out noise. So LIGO and other ground-based gravitational wave detectors are limited between detecting gravitational waves of the frequency band between 10 hertz and 10 kilohertz approximately. And this is because of two reasons. The first is there's arm length limitations. So you can kind of see in these pictures, these interferometers have two arm lengths, but you know, the Earth is full of mountains and we don't have infinitely flat surfaces. And these chambers that have the interferometry measurement are all under vacuum. And so there is some sort of a limit as to how long we can make these arm lengths. So that's one. And the other is terrestrial gravity gradient noise, which is just a fancy term for any sort of gravity or seismic activity actually does influence the measurement so far as to limit us to that frequency band that I mentioned. So the first gravitational wave wasn't actually observed until 2015. So up until 6 years ago, gravitational waves was only a theorized and predicted thing, and it wasn't actually physically measured until 2015, where a binary black hole merger was detected in both detectors in Washington and Louisiana. The particular incident was 1.3 billion light years away. And you can kind of see in these mass numbers, we have really massive black holes that merged, and the resulting total mass after merge is lower by about 3 solar masses than the two before they combined. And so that 3 times the solar mass was converted into a gravitational wave signal. And actually, this measurement, along with subsequent measurements after this, basically motivated LIGO, the inventors, to win the Nobel Prize in 2017, which is pretty cool. Another really monumental moment for LIGO and for the gravitational wave community was this first multi-messenger observation, where a binary neutron star merger was detected. And because it's a binary neutron star, it also emits electromagnetic radiation. And so not only was ground-based detectors, gravitational wave detectors, able to detect it, but also the gamma ray burst monitor Fermi and other electromagnetic radiation telescopes were able to observe this event. And because of that, they were able to localize where in the sky the event happened, and then all these telescopes was able to detect what remnant radiation was coming from this source. So this is 2017, 4 years ago, really new way of doing astronomy and science by detecting an event's gravitational waves and then also detecting the electromagnetic radiation that it inputs. So it's also a really cool thing for the community. So how exactly does interferometry work and how LIGO works? Some of you may already know this, but for those who do not, I'll just give a brief overview. The type of interferometer that LIGO and Lisa will also use is a Michelson-like interferometer. And basically, an interferometer can really precisely measure the change in position between 2 free falling points. So if you look at the schematic here, if the 2 mirrors here change relative to one another, it will be detected with the interferometer, and we can actually determine what those really small changes in distance are. So have this really helpful animation here, where there's a beam splitter and laser light is exchanged between these mirrors and combined back onto a photodetector receiver. And what happens is if the distances are perfectly as they should be, no gravitational wave is passing through, they will destructively interfere and produce no light on the detector, as you can kind of see in this. You see the waveforms destructively interfering. But if those distances change relative to one another ever so slightly, what you'll see is kind of this pulse of light. You can see these waveforms are slightly not completely out of phase with one another. And so the intensity of that laser light signal is how we can precisely determine what the distance difference is over time. Okay. So the LISA mission. This is where we're trying to detect these gravitational waves, but in space. If we're in space, we can detect a really rich frequency range of 0.1 millihertz to 1 hertz, so a lot lower frequencies than LIGO. It's composed of 3 drag-free spacecraft flying in this equilateral triangle formation, following the Earth in orbit around the sun, as you see in this animation. Each spacecraft is 2.5 million kilometers apart, so they're super far apart, actually making this the largest instrument that humankind has ever built. And here, if you look at one of the spacecraft, there's 3, but the one here is composed of 2 telescopes that exchange and receive laser interferometry measurements from the fellow adjacent spacecraft. So each spacecraft has 2 of these telescopes for the 2 arm lengths. And then you'll see in the graphic, things kind of zoom in to show the optics here of the telescope. And then just behind that, we have the optical bench, which in and of itself is a huge endeavor to produce the optics and make this optical bench as precise as the measurement needs to be. I believe it takes almost 6 months to manufacture one of these. And then after the optical bench, we have what we call the inertial sensor. And within the inertial sensor is a test mass. And you can see the endpoints for the interferometry are made based on the location of this test mass. And so not only is the test mass used for the interferometry measurement, but it also helps to enable this what we call drag-free control. So using capacitive inertial sensors, the spacecraft can fire its microthrusters to orient itself around this test mass. This sensor, this inertial sensor featured here is the bulk of what my work has been at the University of Florida, is a system for that. So I'm talking about these different frequency bands of LIGO and LISA. Where does this kind of land on the types of gravitational wave sources that are out there? So here we kind of have a helpful graphic of the types of gravitational wave sources there are. Here at the top, we have, it's theorized that we can potentially detect signatures of the Big Bang by detecting gravitational waves. And we have all these different types of sources: supermassive black hole binaries, neutron stars, binary mergers, compact binaries. And LIGO can really only detect these really large merger events. But LISA here will be able to detect this really rich frequency band that kind of contains all of these different types of sources. The pulsar timing community is, trying to detect gravitational waves at much lower frequencies. Those observations are ongoing, but as far as my knowledge is to date, they haven't been able to conclusively detect one, but they're hopeful. And basically what they do is they look at the beat note pulsar timing of, light stars that, change their brightness in a very cyclical motion, in hopes that if a gravitational wave were to pass through, there would be some time delay in the flux differences. And so that community is trying to detect gravitational waves in that way. But yeah, LISA, a space-based gravitational wave observatory, is needed to access this particular frequency band. And so, yeah, just talking about different frequency bands, you can kind of see this graph of the projected noise performance of LISA. That's what this dotted black line and pink line are. And basically, everything that's designed for this mission must keep the noise below this overall requirement. And that means that all the subsystems have to do their part to eliminate the noise, so that we can make all of these great detections. And then this graph on the right, you can kind of see the sensitivity of LIGO and LISA next to each other. So LIGO is in the orange and LISA is in the pink. And you can see that LISA is going to be able to detect these supermassive black hole mergers that are starting the in-spiral stage, which is really cool, because LISA, once it flies and it's operational, can signal to LIGO, hey, there's this in-spiral, we're predicting that it's going to merge in X number of days or months or even years. This is where we expect the coalescence frequency to be. So LIGO can actually tune their sensor to be more sensitive in the particular predicted, coalescing frequency. But yeah, so we have some multi detector observations that can happen with this, along with a lot of other things. So again, the strain sensitivity requirement for LISA is so precise here. Basically is, I believe, 1/10 of a width of an atom at 1 millihertz level of precision. And so it's a big undertaking. We have the largest instrument that humankind has ever built, down to the sensitivity of, like a atomic level. So how is this going to happen? How do we achieve this? Well, first and foremost, it's from all of the scientists and engineers that are working on LISA that comprised what's called the LISA Consortium. This is at a meeting that we all had at the University of Florida campus. This is before COVID in 2019. I am right here on the left, top left, and my PhD advisor and other people that I've worked with, and a lot of our European Space Agency folks are on this in this picture. So the LISA project is an ESA-led mission. So European Space Agency has had the primary authority over it, but NASA is a major junior partner. I believe the Japanese Space Agency is also contributing some to the mission, but NASA is contributing about 20% in a technology contribution. And we're developing these technologies to TRL-6. And so different NASA centers are kind of tasked with different technologies, although I believe that the phase measurement, interferometry, the micropropulsion system, and the laser might have changed who's assigned to that in the last 2 years. But I do know that the telescope that Goddard and the University of Florida Physics Department is developing and the charge management system that my lab was developing are big contributions to NASA's part of this ESA-led mission. So here's kind of a CAD model of the different aspects of the instrument. We have the telescope, the optical bench, and then the inertial sensor is contained in this vacuum chamber with a test mass inside of it. And the charge management system for this inertial sensor is what the Precision Space System Lab at University of Florida worked on. So what our inertial sensor is called is the gravitational reference sensor, or GRS, and it's composed of a free-floating test mass. So you can kind of see here in this graphic what it looks like in regards to its vacuum chamber right there. And if we zoom in, we have the test mass that acts not only as the endpoints for the interferometry, but also as a position anchor to enable drag-free control. It's composed of a gold-platinum alloy, which is chosen because it's dense and non-magnetic. And then it's shielded from disturbances due to radiation and other gravitational forces through its housing, and actually shielded through the whole spacecraft itself from any drag that spacecraft's under. The spacecraft motion is governed by just the motion of the test mass, and so that helps to eliminate a lot of movement that's not due to gravitational waves. And it detects really precisely the position of the test mass via its capacitance electrodes that kind of surround the test mass and compose the housing. And it basically forms a capacitor with the surface of the test mass and these electrodes to do sensing. But you can also actuate and inject voltages into the system through these electrodes as well. This helps if the test mass needs to be moved, or we can also inject signals, as I'll talk about later, to perform the key functions for this instrument. Everything is coated in gold, the test mass, and all the surrounding housing. This is chosen because of gold's homogeneous electrostatics, and it also makes a nice smooth reflection surface for the interferometry beam. So just a bit into drag-free control, how it works exactly. The goal of drag-free control is to enable the spacecraft to maintain a purely geodesic orbit, which means a purely gravitational orbit. This sensor acts as an accelerometer, so it is precisely measuring the relative position of the test mass over time through its capacitance electrodes, as I just talked about. So as the test mass moves, it's able to really precisely determine its position. And then this drag-free compensation allows the spacecraft to follow the free-floating test mass that should be ideally shielded from all non-gravitational forces. However, a lot of external forces in the LISA frequency band can disrupt the test mass's geodesic orbit. And one really big source of that noise is charge buildup on the test mass due to cosmic rays and solar particles that are not shielded from the spacecraft, that actually passes through the spacecraft and lands on the test mass. So therefore, to mitigate this source of noise, we need the charge management system, or CMS for short. Because charges do build up on the test mass, we need to think about what types of forces this can induce. So the magnetic field forces are negligible due to the material properties that we chose for the test mass. But the Coulomb forces, the electric field forces, are non-negligible. And so to kind of illustrate this, if we have radiation from the space environment building up on the spacecraft, but some do pass onto the test mass, if left over time, it will start to interact with existing electric fields within the gravitational reference sensor, and the test mass will start to move due to these this non-gravitational force, right? So looking at the Coulomb law equation here, taking it in the sensitive X measurement direction of the interferometry, we have two parts. We have Q, the charge of the test mass, and capital E, the electric field that's present. And both these terms have a DC component, or Q naught, and also a noisy time frequency dependent component, delta Q. So we put these back into the Coulomb law equation. We're left with this four-term equation that basically I've done this all to kind of show the main factors that influence an in-band frequency noise contribution. So that are these two middle terms here, where we have a present electric field multiplied by maybe some really small, minute noise in the charge, but when they're multiplied together, they can produce this in-band frequency noise. And then consequently, if the charge of the test mass is left to build up in term 3 circled in green, that can couple with the noisy electric fields present and also produce an in-band noise contribution. So this happens when the test mass potential is at above or below 70 millivolts. So you can think we need to keep the charge of the test mass relative to the housing pretty as close to 0 volts as we can and not exceeding 70 millivolts. So to do that, past missions that have flown space inertial sensors have sometimes used a really thin conductive wire to discharge the test mass passively. But because of the strict noise requirements of LISA, this method wouldn't do. So we need a contact-free method of getting the charge off the test mass. And so we can exploit the photoelectric effect, a contact-free method of discharge, where UV light is shining on these gold-coated surfaces. And because the work function of gold-coated surfaces is less than the photon energy, the UV light photons actually have enough energy to eject photoelectrons. As mentioned, UV light on the wavelengths that UV light has is a perfect candidate to facilitate this discharge with the gold-coated surfaces. Okay, so this is complicated, right? We have very strict noise requirements. We have a lot of systems going on to keep the charge very close to 0 volts, even despite a really radiation-heavy space environment, because LISA is way far away from the Earth and the Earth's atmosphere. It's subject to more radiation than maybe like a low Earth orbit mission would be. It has some protection there. So LISA Pathfinder flew from 2015 to 2017, basically to test a lot of key technologies to LISA. One important one was charge management system to kind of ensure, does this perform in space? Will this perform to the level that we need it to for LISA to be successful? And this mission was really successful overall, its performance well exceeded expectation, which was great. And if you think about the timeline of this mission and its success happened right after the first gravitational wave was detected with LIGO in 2015. So this mission, although it's been around in conception for the last 20 years, really gained a ton of momentum starting in 2015, 2016 with the gravitational waves measurement and with the success of LISA Pathfinder. I really like this picture here on the far right. You can see the LISA Pathfinder module. It was just one spacecraft, kind of set in its rocket and as a payload prior to launch, and you can kind of see the size difference in comparison to this person that's standing here in the room. But yeah, you can see the performance of LISA Pathfinder. The first measurement, the moment that they turned it on and took a measurement was the blue curve, which was great, well exceeded the Pathfinder requirements, getting close to LISA requirements. And then with tuning and calibration, things like that, almost a year later, they were able to achieve this noise performance, which is much lower even than the LISA requirements. This is really good. So on LISA Pathfinder, the charge management system consisted of mercury lamps for the UV light source. And it also implemented only really basic charge control methods where the test mass charge was left to charge up to 70 millivolts. So the space radiation environment actually had a positive charge up of the test mass. And then after about 2 weeks time, when the charge got to 70 millivolts, a bunch of UV light flooded the system, discharged the test mass. But unfortunately, because so much UV light was shining into the system and everything, the science mode was not able to start. So we only really got good data within 2-week-long stretches of time. So this kind of led to a motivation of developing more advanced charge control methods that potentially would mean that we wouldn't have to stop the science measurement at all. And if you think about it, it would actually let us access lower frequencies too, if we can kind of push the on-time ability of LISA. So the charge management system at the University of Florida consists of a number of main key efforts. The first is actually validating UV LEDs for spaceflight. So this is one of the ways that the system's becoming more advanced. We're going to fly UV LEDs instead of these mercury lamps for the UV light source. Are chosen because they're a lot lighter, but the main thing is that they can be duty cycled, pulsed to limit the amount of UV power that they shine into the system. As I mentioned before, these mercury lamps, they were on and shined a huge amount of UV light into the system, and that actually produced enough noise to be above what the noise performance should be. So we're trying to get to lower UV light powers, and so we need to validate these UV LEDs for the mission and for space flight. That's one big effort. Another effort is developing the charge management device, or a CMD as we call it. So that's basically designing and testing the flight hardware to power the UV LEDs in the way that they're needed to perform these advanced charge control modes with lower UV light powers to try to keep science mode on at all times. A third main effort is a gravitational reference sensor experiment testing site. We have a space-like experimental test bed called the torsion pendulum that we've been able to run a lot of experience on since like 2014, 2015 timeline to test these gravitational reference sensor technologies. So I'll kind of go into each of these things, just briefly touch on the work that we've been doing. So for the UV LED performance and lifetime validation, the mission right now is, baseline is a 4-year-long mission with possible 6+ years of extension. So if all goes well, we'd love to have this instrument on for 10 years or maybe even longer. That's a really long time to be in space. So we basically need to understand, will these LEDs, provide UV light for this amount of time, subject to a radiation environment, which is a huge question that NASA has and that we're trying to answer. So this is kind of what a UV LED looks like. It's in a TO39 can. It's quite small. And this is kind of the lifetime testing setup that we've developed at the University of Florida, where we have thermal control and different units. Here you can see there's 12 units that hold 8 LEDs each, and as well as a whole software system designed to command and receive data from each and every LED individually. So we can basically run 96 LEDs at one given time. We had a first round of lifetime testing that occurred for a year, was able to get some results for that. And then I'm right now undergoing the second round of lifetime testing. And the idea is to monitor the performance throughout and then extrapolate the degradation of the LEDs over 10 years, since we don't have the time to run them for 10 years and see how they do, right? So that's the basics of what's going on in this effort. So the second main effort, the charge management device, here's just a little bit of information about what this system is composed of. It contains the UV light sources themselves, so the LEDs. All the electronics need to run them, analog and digital. The software design in order to run them with these advanced charge control methods in mind, as well as a fiber optic harness that will direct the UV light from the charge management device all the way to the gravitational reference sensor. So here you can kind of see our basic outline for our CMD. So we have a power board, a control board that manages all the software, and then kind of this modular design with these analog current drivers to run these UV LEDs. And we have a lot of redundancy contained in the system. A lot of reliability analysis are being done right now with our University of Florida's industrial partner, FiberTech, which is they're basically helping us get from the conception up to the engineering flight unit. One of the things we're doing is we're looking into the redundancy scheme to make sure that we can ensure that for at least for the 4 years, we have a very high probability that everything's going to work. And so even in this one unit, there's redundancy of the UV LEDs that are needed. Each gravitational reference sensor has 3 UV light ports. And you can kind of see this illustrated here in this spacecraft redundancy scheme. Each spacecraft has 2 gravitational reference sensors for the 2 optical benches and 2 telescopes for the 2 arm lengths, right? And each GRS has 3 UV light injection ports. And so you can kind of see, even for the 3 UV light injection ports, one unit has 2 times redundancy for the LEDs that feed those different injection ports. And the idea is to have 2 charge management devices per spacecraft. So there's already another level of redundancy on top of that. So very redundant. We really need to make sure this works. It's an expensive mission. This isn't quite like oh, we'll launch it in a year or 2, see if it works, and if it doesn't, make a modification. No, this one has to work. So that's why we have such redundancy here. So here's just some pictures of what our TRL4 unit looked like that we completed at the end of 2018. And my personal contribution was developing the analog current driver for the UV LEDs. And I worked on a team of 2 other people to build this unit. We had a digital and software lead, and then a mechanical and optics design lead that developed this this optomechanical assembly to fiber couple the UV light into a fiber. And you can kind of see this is a unit all closed up. And we have 3 units of these in existence. One of them is actually in Italy. So we have the Italy team is developing the gravitational reference sensor itself. We're developing the charge management system. So we need a lot of collaboration. So we actually gave them one of these TRL4 units to run on their pendulum that they have for their gravitational reference sensor development. And it was the first piece of NASA technology that was delivered to ESA in relation to the LISA mission. And we were able to do that the summer of 2019. So this is pretty cool. And you can see here the unit is sitting there and have a little Italian flag banner. So yeah, it's one sitting in Italy, and the other one's being used on our torsion pendulum facility. So the TRL5 build was completed at the end of 2020. Even despite COVID, we were able to finish design on this with a few setbacks. And this is designed with a direct path to flight. So you can see here's the unit sitting in a vacuum chamber. You can see it looks a lot more like a flight-like unit. We have the main and redundant sides of the unit here with 6 UV LEDs on this side and 6 on this side. You can kind of see with these SMA fiber feed-throughs. This was designed with a direct path to flight, not only in the mechanical model, but also in the electronics. So every single chip in this unit has a space qualified equivalent. And every board actually has the footprint of that space qualified equivalent. So we know that the size and the form factor, will be okay for flight. It's not like we're going to add these chips that are all double in size and have to change the size of the PCBs too late in the game, while we're already doing all of these testing on the mechanical structure of the unit, right? So this unit underwent a pretty extensive TVAC test. We had a lot of 60-hour measurement tests because we're looking at noise performance at such low frequencies. So the testing campaign took a pretty long time to do this past spring and summer. And then the unit also underwent vibration and shock testing just this August. And we just had our TRL5 assessment in this September. So I was able to attend that assessment just before starting my job here at Virginia Tech. So that was neat to be a part of. And right now, TRL6 has been in development for about the past year with our industrial partner Fibertech. And the goal of that is to be completed in 2022. And so they're kind of taking this design towards flight and engineering maturation. So just to briefly touch on the third item that the University of Florida is working on to help with the charge management system is this gravitational reference sensor experiment testbed, which is what we call the torsion pendulum. This is a really neat piece of technology that simulates free fall in 1 degree of freedom. This instrument was made in Italy, and then we modeled our pendulum very similarly after that design. And you can kind of see in this CAD model on the right, it's composed of this really long tungsten, thin, strong fiber. And at the end of it is this cross arm assembly, right? So you can kind of see a picture of it here in the middle. And so while it's hanging from this really thin but strong wire, and as it's left to rotate in this X direction, it basically is not encountering any spring constant because it's so small to restore itself to its original position. So that's why the rotation direction is essentially in free fall in that 1 degree of freedom. And the test masses are hollow to kind of help to limit the weight of it. And there's only, they're at all 4 ends to help with balancing it, but we have 2 different gravitational reference sensors. At one end, we have a simplified one, and another end, we have a LISA-like one with all the electrode configuration that the LISA sensor will have. And the test mass position can be read out with a capacitive readout, but also with a laser interferometer readout that we've recently, in the last 2 years, was able to upgrade. That was one of our graduate student projects. That performs a lot better in terms of position accuracy. So here it is in its vacuum chamber, made for the torsion pendulum, and we actually have it surrounded in this thermal room for passive temperature stabilization. As you might know, temperature fluctuations and differences can influence things noise-wise, especially at low frequencies. So adding this kind of insulating thermal room significantly helped our performance, actually, for the low frequencies especially. So again, like I mentioned, we have a simplified GRS. You can see a picture of it here at one end, here on the left, where there's only 1 electrode per face. And then we have a LISA-like GRS, which was implemented like 2 or 3 years ago, I believe, that has all of the crazy electrode configuration that LISA has. And then we also have 3 different UV light injection ports to test different charge management schemes, which I'll briefly touch on before concluding this presentation. So this is also the noise performance of the interferometer. You can kind of the torsion pendulum. The red is the interferometry measurement, and then the blue is the capacitive. The capacitive does perform a little bit better at really low frequencies. And you can compare it to the LISA acceleration requirement, which is in pink. So it's about a factor of 100 higher than the LISA requirement, but for a ground-based test bed, this is doing quite well. So this is an excellent test bed for LISA technology for us on the ground without having to fly anything in space. So, okay, charge control modes. Again, just going to briefly touch on this, but this is a big chunk of what I developed for my dissertation. But the baseline discharge mode is what we call a DC, or continuous UV light discharge. So basically, the potential of the test mass is controllable with whatever UV light injection port you use, and you just shine the light continuously. So if you want to move electrons from the housing to the test mass, you shine your UV light onto the housing, and that would force electrons to be ejected from that surface and land therefore on the test mass. So you can see with the housing port being used, the test mass charge was left to decline. And then if you wanted to bring the test mass charge up, you would shine the light on the test mass, eject the electrons from that surface, and bring its net potential up. And so that's kind of what you see in this other one. And you can kind of see that based on the amount of UV light that you shine into the system and the geometry of the source, you kind of are left with this equilibrium point, right? Where the charge kind of levels out to these different equilibrium points. And so we can kind of utilize some of that, the fact that they do settle to equilibrium points in these more advanced methods, which we call AC charge control or pulse charge control. So instead of shining light continuously in DC, we can pulse the UV light. We can pulse the UV light in or out of phase with an already existing electric field, a high frequency electric field present in a gravitational reference sensor for the actuation and sensing. And this particular frequency is 100 kilohertz. And again, just kind of arbitrarily chosen to push outside of the frequency band of the LISA measurement. And so whether you shine the light more in phase or more out of phase, regardless of whatever injection port you use, you can kind of facilitate the photoelectron current direction. And just a little bit of the heritage of the hardware to do this. This was a very first generation pure analog circuit. We actually used trim pots to change the phase and the duty cycle of the UV light pulses, albeit not perfectly, but was able to achieve it. And then with the TRL4 unit finish with that build, they have a lot more of a precise way and LabVIEW instrument basically to run this unit, have a lot nicer pulse shapes and things like that. So I was a big part of this technology development from this baseline to the TRL4 unit for the pendulum to do some of these more pulsed and advanced charge control methods. So to conclude, the future for LISA is a fully funded mission. Right now, it's currently in phase A, which is mission formulation. The mission adoption will happen in 2023. I believe this was pushed back a year because of COVID. And after that point, the design will be frozen. So there's a big push to get to TRL6 by this time. And right now, the launch is scheduled for 2034, year 2034. And they keep changing this date. Sometimes it's a few years sooner, sometimes it's just a year after, but they're kind of hoping in the early 2030s to get LISA launched. And LISA will have an about 2-year cruise to its Earth trailing orbit. That's how long it's going to take for it to get into position and get it aligned and everything. A 4-year nominal mission with a potential 6+ year extension. So be on the lookout in the news in the 2030s for the launch of LISA and for the hopeful success of LISA. The hope and the plan is the moment that LISA turns on, it'll be able to detect a bunch of different gravitational wave sources. And there's actually research groups right now developing all of the data analysis now so that we can handle the amount of data that we're going to get once LISA turns on. Actually, that's a large bit of what the French do as part of the consortium. The French are all into the data analysis. So I just want to acknowledge the funding sources that made the work at the University of Florida possible, as well as my PhD research. Want to thank the LISA Consortium for their work on LISA as a whole, as well as my advisor, John Conklin, and then research scientist in my group, Peter Wass, who contributed significantly to LISA Pathfinder, and he's been a huge asset to my PhD research. And then my whole lab, who this is a very interdisciplinary project. So I worked with a lot of graduate students and postdocs to make a lot of this stuff possible. So just acknowledgement to all of them. Thank you for your time and your attention. If you have any questions, feel free to email me. This is my VT email here at the end. Yeah, I'd be happy to talk about this or other things. But I hope you enjoyed this presentation, and I'm really looking forward to the ways that I can help out the Space VT group in the coming days. So thanks, everyone.
Thank you so much, Sam. Yeah, it's a very informative presentation. I do learn a lot. I also have a lot to digest as well. Yeah, since I'm not an expert on these electronics or technologies. So yeah, does anyone have any questions for Sam?
I mean, I thought this was a really interesting presentation, but the first thing I can't help but ask about, I mean, 12 years to launch now, and you've been at it a few years. There's nothing comparable to that in NASA that I know of. Apollo wasn't even that long. And, you know, the TRLs, the mission is starting from very low TRL technology, maturing it, and then flying it. I can't think of anything similar. I just think it's really amazing the way they're going about this.
Yeah, I mean, something to point out, I think the charge management system is one of the few technologies that have really has had this recent path to TRL 6. And I think it's because of the result of LISA Pathfinder, you know, kind of realizing we do need to reform the way that this is done. And then with UV LEDs hitting more commercial markets, I think that those things were kind of a more recent thing that led ESA and NASA to both be like, okay, let's get this technology up and going pretty quick. But most of the optics and things have been flight qualified through the LISA Pathfinder mission. But you're right. With that all being said, there is a lot of development, and a big reason why it's taking so long to launch is because of how long it's going to take to manufacture everything. As I mentioned, I think right now it takes 6 months to manufacture one optical bench, and they need 6 at least. So I think that they're just trying to allow enough time. Airbus is the engineering company that's going to be building everything, but allowing enough time for that to happen. And it's so many places are involved in this mission, and so even just that, I think that they're also planning on that taking some time. Yeah. And the way that Europeans do things is a little bit different than the way that Americans do things. So I think a bit of that is also coming into the timeline, along with the other things that I mentioned.
Yeah. Well, I didn't mean it as a criticism. I mean, it shows how important they think it is, because I just can't picture NASA doing this unless maybe for the Webb telescope or something. But even then, that's a long development. Could you say something about what it'll be like to operate this? Do they have a list of targets they're going to monitor, and how long do they spend on any one? What's it like to actually do the observations?
Yeah, so the idea of the observation is to just kind of be continually surveying different parts of the sky as this this kind of triangle formation spacecraft kind of like spins over itself and orbits the Earth. And so it doesn't have the type of capacity to be like, oh, we want to point it in this direction now, so we're going to change the orbit completely. It's more like a continual survey of the sky, and it's kind of seeing as things develop. So operation wise, like I mentioned before, I believe that the data group in France, and there's some scientists at Goddard actually working on this too. They're developing a lot of the algorithms and things now, so there can kind of be kind of quick recovery from measurement to interpretive science results, and you know, kind of have a bit of a chain of reaction that way. In regards to charge management system operation, I believe there's going to need to be a control room who's, you know, making decisions on that. But the goal of I guess my research group and this more advanced method is to try to make this system more or less passively stable, so you don't always need someone changing like UV light parameters and things like that. That once initial calibration happens, that the system will more or less be able to run on its own unless if something breaks. But I'm not entirely sure about the other subsystems, how they will operate, but that's a little bit for the charge management system.
Okay. Sounds good. Well, thank you for that. And by the way, welcome to Space at VT.
Thank you. Thanks, Dr. Bailey.
Yeah, does anyone else have more questions for Sam?
Hello, yeah, it's Mike here. Yeah, thanks for that fascinating talk. I'm just amazed by the precision that's required here with this measurement and the scale in which you're going to achieve it. Maybe you covered this. How many gravity wave events have been detected with LIGO? How often does that happen?
Yeah, that's a good question. I haven't been up to date with the measurements, but I believe it happens like 3 to 5 a year about now. And that's, I think it was online for a year or two before it was detecting that first wave in 2015. And then since 2015, a lot of tech improvements have been made to kind of make it so we can detect more and more. So they call that advanced LIGO, or like a little lowercase a LIGO. And that's a NSF funded project. So there's a lot of new technologies that are still being implemented into this interferometer so that we can bring the noise floor low and detect more and more. But my understanding is that it's about 3 to 5 a year that is able to detect, but that might have changed in the last 2 years. A few years ago, that was my understanding of it. So,
yeah, and with Lisa, do you have an idea of how much more often, because of the the different frequency range in which you're sensitive?
Right. So the idea with Lisa, what they're kind of predicting is that it's always going to be detecting some sort of gravitational wave signal. And then a big reason for that is because it's going to be able to detect black holes that are starting to coalesce and come together before the merger event. And so these can happen days, months, years timescale. So if that's slowly increasing over time and Lisa can see that, then it's always going to be one of the many signals there. Whereas LIGO really can only detect the moment that they coalesce and form one object and have a really large frequency burst, large in magnitude and high in frequency type of event. So yeah, the idea, especially if there's also signatures of the Big Bang in some of the gravitational wave signal, the idea is that at all times there's going to be gravitational wave signals and events and things to detect. So it's going to be a lot more busy, I guess, than LIGO.
Neat. Thank you.
Yeah.
Yeah, I have a relevant question, Sam. So you mentioned that Lisa can talk to LIGO, kind of say like after a certain amount of time, you should be able to detect this. Do you know what's the timeline, like what time delay between like being observed by Lisa and then LIGO is going to observe something like that? Is that a typical number or it varies from source to source?
Yeah, so it travels, gravitational waves travel at approximately the speed of light. It's like a few seconds difference. Like if you recall it, when I have the gamma ray monitor and the gravitational waves hit like a second and a half before the gamma ray burst. And so, yeah, the gravitational waves travel at about the speed of light. So if something happened 1.3 billion light years away, then it's going to take 1.3 billion light years for it to get to us.
Yeah, but you mentioned like because of the frequency difference, like it can be observed by Lisa at the beginning stage, but then for the LIGO, you can only observe when that occurred. So there must be a time difference. Is that like a few days or years or something like that? It's curious.
Right, that's a good question. It depends on the source. Some sources, especially I believe the massive ones will take longer to kind of finish its coalescence. So it's going to go through that frequency range a lot slower than things that aren't as massive or things that are a little closer to us. So it all depends on some of those like astrophysics parameters of the object merging.
Yeah, do we have any model like which can predict like when it's being observed by Lisa at this stage, like after a certain amount of time will be observed by LIGO? Is that capable?
Yeah, I believe so. We kind of have an idea of what types of solar mass sized objects will produce what gravitational waves in what time frame. Okay. And so that was kind of I wonder if I can flip back really fast. That graph that kind of showed all the sources. You can kind of see, here. So you can kind of see here, actually, it even has on the graph, this is great, kind of the time scale here. So the really large objects, the supermassive black holes, the more massive they are, the quicker that they will coalesce. But the objects that are maybe a little smaller in weight, these LIGO type binary black holes, they'll start the coalescence, and then you can kind of see the amount of time based on this of how long it'll take. So it could, LIGO could detect something that will coalesce in a day, or it could detect something that will in 10 years. It just depends on all of those things. So.
Okay, I see. Thank you.
I have a question.
Okay, go ahead.
Yeah. First of all, like, great presentation, and there's certainly a lot to digest on. I have a little bit question that is like a little bit off from what you presented. Like, is there any particular place where you would like to place the satellite in, like the L1 or L2 that you talked about, where you would be detecting the gravitational waves better? And how do you work with the mission planners and who figure out the orbital mechanics of things of the spacecraft, that the trajectory that it will take at the end?
Yeah, so I'm not as familiar with the science behind where we're expecting more gravitational wave detections. I know in terms of electromagnetic radiation, there are certain parts of the sky that are better to observe certain stars rather than others. Like if we can get out of our galaxy versus having to look through our galaxy, But I believe because gravitational waves pass through space-time more or less unhindered, that it's more a function of where the signals are rather than a spot where things will be more sensitive, right? And in regards to where the detector is and what part of the sky it's pointing to, because of this orbit, because of this orbit, it's basically observing the part of the sky that's orthogonal to the plane that the laser links make. And just over the course of the year, it's going to be kind of surveying the whole sky, whole 360 degrees. That was a dynamics decision that someone made at some point, and what orbits that they would be in to kind of achieve this. But yeah, I guess hopefully that answers your question. But it's not like we're going to be able to be like, oh, we want to move it this way, so we'll put it in this part of the sky and just let it sit there, because it's in this orbit around the sun, trailing the Earth. It's a bit more dynamic than that. It'll be moving constantly. So.
Yeah, got it. This slide makes it clear because I had made this slide before. Sorry.
Right.
So,
no, that's okay.
That's good.
Yeah.
Thank you so much.
Okay, so any more questions? I think we come to 1 hour at the end of the meeting. And if there's no more questions, so I think we can conclude the session. And thank you everyone for a great discussion. And thank you, Sam, for a great presentation. So
yeah, thank you. And here's my email again. If you feel free to reach out for anything. If you have any further questions, I'd be happy to answer.
Sure. Okay, so probably see you guys like in 2 weeks or 1 month, depends on our speaker next time. So bye.
Bye. Thank you, Sam. Thank you all.
Bye. Thanks, everyone.
Thank you.
Thank you.